Okay. Hello, everyone again. I'm very sure that everyone is quite tired, and which is not so bad because this session is very easy to follow. Um, so if you're already familiar with CUDA, this shouldn't be anything new to you. And if you're not familiar, then I will just introduce um, the most important keywords. And then tomorrow we will talk about a little bit of optimization. So let's see. We will just start. Um, in this slide, I just present the evolution of of the specs of the last three NVIDIA GPU architectures. Okay, I didn't say that I'm going to talk about CUDA. So CUDA is a NVIDIA technology and for programming GPUs. It's pretty much in the same line that OpenCL that was just presented with its Python wrapper. But and actually there is another CUDA Python wrapper also developed by Andreas that is available and I find very useful. And this is basically a comparison between the different specs on the GPUs. It moves from the G80 that is roughly 2007 to the current generation that is Fermi, and it went from 700 million transistors to 3 billion G. So it's kind of the number of logic elements that you can find in the chip has grown quite a bit, and also the functionality that you saw. I remember working with the G80 was very limited, and right now you have a GPU chip that is able to do pretty much anything that you need for scientific calculations. You have dual precision floating point capability. You have single precision floating point capability. You also have special function units that can compute special functions, for example, exponential, cosines. Another key words to keep in mind is the word warp here. You have shared memory. The latest version of Fermi. Okay, the latest version of Fermi has L1 cache and L2 cache. So this really improves all the codes are bandwidth limited. Anything that requires quite a lot of memory transactions. The cache memory is very important to get good performance, or at least to remediate some of the problems of having high latency. Another thing that is really important, and it was just introduced in the latest version of Fermi, is ECC memory support. And this is what actually means is that many times while you're doing calculations and data is being moved from the memory, from the chip to the GPU, it can happen that some of these bits can flip. So when it should be a 1, for some reason it arrives at 0. And what the ECC does is to check when that error happens and redo the transfer so that you don't get the error. Until very recently, GT200 GPUs, you didn't have this feature. And it's actually not so important when you only have one GPU or maybe two GPUs. But if you imagine that the latest supercomputers are composed by a few hundreds of this GPU, and each of them maybe fail once every million hours or so. You get that if you have 1,000 GPUs, and you have a million hours of failing only per one card, then the whole system is going to fail once every 1,000 hours of calculations. And if you're running a very long job, that's actually quite frequent. And that can destroy your whole calculation. So this ECC feature is quite important if you have a big computer. For example, if you have heard of Tianhe, the new #1 supercomputer that is currently in China. And it has 8,000 GPUs, I believe. And for that number, it's very significant to have a lot of controls for when the system, the things fail, because they're going to fail. So I think that you already heard about a very good case of OpenCL. And I'm here just to advocate for CUDA. And so far, there is no decision of what's going to be the technology that is going to be adopted by all the people that is working on GPU computing. Some people is pushing for OpenCL, some people is pushing for CUDA, and I personally like to see what is going to happen. I don't really care which one wins. But I'm much more familiar with CUDA than with OpenCL, so this is the one that I'm going to present. At the very core of these two technologies, the problem is the same. So basically what you learn here is readily applicable to the other problem. And as we were discussing, or at least as I presented in the first lecture, and the same case what was made in the subsequent presentations, I think that the most important part when you are developing a piece of code is the algorithm that you're going to use. So most of the time that you're going to spend on developing code is going to be used on obtaining an algorithm that can actually scale be applicable and get a solution in a reasonable amount of time for the problem that you have. And so that actually means that the amount of coding that you will do is kind of not so big in terms of that you will be hacking code. Probably what you will be spending a lot of time is doing debugging and tuning. But that happens just after you already have an idea of what you want to do on the GPU and what's the general design of your algorithm and your application. So what actually happens when you're doing development is that you have a iteration cycle where you go through your first evaluation of the code and you already know what you want to do. It's just that you need to tune this code so that it runs faster. And you change some things, some of the calculations, the order of them, or the type of calculations that you're performing. You evaluate the performance of your code again, and according to the performance and the new bottlenecks that you see in your code, you do extra modifications and iterate again. So if you remember the presentation of Andreas, where he has his Python wrapper over OpenCL, one of the biggest advantages that I see for this kind of technologies where you have automatic code, you can generate code out of a string of C, is that the whole cycle for development is really accelerated. So you can do a lot of development very fast just by rapidly iterating through Python. So you can have a whole test setup that is going to test your specific application and a specific kernel that you want to tune. And you're working this directly from Python. And you are able to program or optimize this code for a set of data sets that you have for CUDA. And you isolate your problem of the GPU programming to the single problem test that you have. And then you run it through Python and iterate over this instead of having to work with your whole application. And that's a very nice way to do the development. And you, of course, can do this now with CUDA and OpenCL by using the Python wrappers that are available, courtesy of Andreas. So, okay, what are the strong points of CUDA, or at least the ones that I think that are strong? The first one is that it gives you an abstraction from the hardware. And this actually means that it's kind of opposite of what I already said, but it abstracts you from the hardware in the meaning that you don't actually need to work exactly with each piece of hardware as like a card. What you do is that it gives you an idea of the features that the hardware has at an abstract layer. So, for example, it's from one generation of a GPU to the next. They change something in the hardware. They keep the same abstraction layer, and you have forward comparable pieces of code. So once that you develop for this CUDA model, it will keep working in future generations. What they do, though, is that they increase the set of features that CUDA supports between different generations. So as the hardware advances, you can get new features, for example, atomic operations, and some other features that are appearing with each of the CUDA generations. And you can see them on the CUDA development guide. Another thing that is very important in CUDA is that you have automatic thread management. So imagine that your application is going to be running something in the order of a few thousand threads concurrently. It's actually not very nice if you have to manage where each of these threads are going to be executed at any given time. And what CUDA does is that it abstracts the problem of having to decide where to launch each of the threads by defining some interface where with the one that you have to deal with these kind of things. And this is a high-level interface that is not related to the hardware. And the reason why you have so many threads on the GPU is because you need a multi-threading, and this is something that I said early today. The main reason why you have this technology is because you need to hide the latency on the GPU, and it's basically the fundamental difference in the design of the GPU compared against the CPU. But the very nice thing of all of this is that this is completely transparent for the programmer. You don't really need to be aware of all these little details that are actually happening under the hood of the different GPU cards, and actually it depends on the driver. And that's another reason why when you change from one version of the driver, of NVIDIA driver, to the other, you can see big differences in performance. It's just that all these little details are being handled by the driver without you having to know about it, are changing it slightly from one version to the other, and you can see sometimes big differences between one version of the driver to the other. Just as an anecdote, in the cluster that we have in Nagasaki, we're actually using quite an old version of the driver just because for the application that we have, it happens to work the best for what we do. But if we upgrade to the newest one, it will actually run slower. And just because of the difference in the implementation for the GPUs that we have. So that's some of the things that are kind of interesting. And the other thing is that we have optimized this code so much at the point that we actually know what's happening at each point at each line of the code. So as soon as we change a little bit the compiler and the library that is doing everything, kind of all the tuning goes bad. So this is the kind of optimizations that we're talking about. Another thing that is very nice about CUDA is that it's very difficult to deadlock. So if you have a program MPI, one of the biggest problems that you have is that many times one thread requires something from another one that requires something from the same thread. So they are kind of all of them waiting for the same thing to happen and nothing happens. Something like that cannot happen in CUDA, mainly because actually it could happen in CUDA if you really try very hard. But by default, all the threads are not they cannot communicate and collaborate between each other outside different block sizes, and I will explain that. So there is no message passing; everything is through shared memory. So these are the main components in terms of programming effort that you need when you want to start working with CUDA. And I think I should repeat this again. I see programming languages just as a tool for expressing what you already have in your head. If you don't have anything here, actually nothing is going to happen there either. So it will save you a lot of time just to sit in front of a piece of paper and see what you really want to do, instead of just jumping straight to the GPU, because performance is not going to arrive magically. It doesn't happen. Programmer effort is once that you have done all the other effort, and which is like 90% of it, getting the algorithm right, getting the whole design right, preparing all the data so that it can go to the kernel. Once that you solve that part, then you jump into the kernel and you have some ideas of you have some expectations of what's the performance that you should get out of your GPU card, because you know how fast the GPU is running, what's the bandwidth that you have. Once that you have that information, you can have some expectations on the performance that you should be seeing out of your code, and you just start coding and optimizing your kernel. So it's basically just a tool, and I find it not the most important part of the discussion when you're talking about GPU computing. And then the programmer effort is mainly analyze the algorithm and expose as much parallelism as you can, because here we're talking about thousands of threads that need to be running concurrently. And then some parameters that you can choose with CUDA is the block size and the number of threads, which are closely related, and I will explain them a bit later. And here the big challenge is to keep the machine busy. Again, we have thousands of threads running at the same time, and you want all of them using the GPU resources as much as possible. So that's your goal, keeping the thing busy. So here are different things that you need to take into consideration when you're keeping your GPU busy. You need to manage your global data. So you have some data that is residing on the global memory. You have some local data that you also want to exploit. Once that you move the data from the global memory to the GPU chip, you want to reuse it as many times as possible. So when you are designing your algorithm, you need to think, okay, this is moving from here to there. How many on what kind of calculations can I do with this data once that is inside the GPU chip? And that could be shared memory or register space. So these are two very fast memories that are within the chip. And everything here, you have not even start coding. You know where are the specs of your system, so you can have some expectations of what's the performance that you should be obtaining. And for this process, where you need to think about how much data is coming in and how much you can eat on the or compute using the streaming processors, you can use the occupancy calculator to get to the balance of what's actually the best number of threads that you need to have on your system to keep it completely busy. So over here, up to this point, I have not even started programming. And okay, here's where we start looking at some of the bits of the CUDA. The first thing is that you have a thread hierarchy, and this thread hierarchy is used to abstract the thread execution, so that you don't need to decide where and which thread is going to run on which processor, a streaming processor. So basically, what happens is that the first thing that you do is that you program a kernel. And a kernel is just a C function, a normal C function, that is going to run as, I guess, as a very lightweight function, or kernel execution, how do you say? A very lightweight thread on your processor, like a CPU, but this is very lightweight, meaning that it's going to use a tiny bits of resources, maybe a few bytes in terms of memory. And ideally, it will do hundreds of calculations per each of these data that are being stored or used in this thread. The big advantage, or how do you know that each thread is which, is that they come with an ID. So some sort of identification that can tell you that this thread is different from another one. And you can use that information to distribute the work that needs to be done. Now, you can, for the same kernel, this is a function that is going to be executed exactly the same for all the threads that are grouped together. You can execute thousands of threads. Oh, this is difficult. I think that for Spanish, TH is not a very easy pronunciation. So you have thousands of threads that can be executed using the same kernel. So the same function is being run by several of these lightweight threads. Now that you have the idea of these threads, you need to organize them somehow so that you can take advantage of the different levels of the memory hierarchy. And they have done it in a very simple way. They just said, we bunch together a group of threads, and we say that this is a block. So that's a thread block, just a bunch of threads. And now the special feature of having a thread block is that all of them can synchronize between each other. So you can tell them that they have to, you know, synchronization is that no one can pass this point until all of them are here. So it's just a checkpoint. And then at a higher level, you have these blocks. And the nice feature is that each of these blocks is going to run on one of the stream processors. And the stream processors is, probably Andreas already explained what's a stream processor, and I already did in the morning. It's just one of these SIMD processors that are the single instruction multiple data kind of basic components of the GPU. And you have many of these SIMD processors. Because of that, you can have many of these blocks, thread blocks, running on a single multiprocessor. And there, of course, there is a limit of how many of these threads can be running at any given time, and that's given by the number of resources that the GPU can handle. But ideally, in a perfect GPU, you can have an infinitely large amount of threads running at any given time. Okay, and this is a thread hierarchy, and this is closely related to the memory hierarchy. And the reason for that is that you need to take advantage of all the little resources that you have available and you squeeze them as much as you can. So there are basically three types of memory within the GPU. You have global memory, you have shared memory, and you have registers. Registers are the local variables that you define within your code, within your function, and those are very, very fast. Actually, it doesn't take any time to access it while you're doing calculations when you access registers. Shared memory is actually almost as fast as registers, and actually the speed of accessing the shared memory compared to the registers depends on the GPU that you're running. So for some GPUs it's faster to use registers, for some other ones it's faster to use shared memory, of course if you don't have collisions, which I won't talk about right now. So this depends on the GPU. And you also have global memory, and this is the large piece of RAM that you have available on the GPU card, and it's the one that you will move the data from the host to the GPU. And once that the data is on the global memory, you will work with this data set as much as you can. Again, as a few presentations ago was being discussed, one of the main issues with getting a good scalability is data movements. Every time that you need to move data from one place to another, the critical point here is the latency at the bandwidth of your connectivity. So I really like analogies, and the best way to see this is imagine that you have two cities and you need to travel between them. And if everyone wants to go to a certain location, they will saturate all the lanes that connect these two cities, and then you run out of bandwidth, and you get a very big. It's very slow to get from one place to the other. It's not very big queue. And then how much time it takes since the point that you leave the city to the other one is the latency that you have, and then latency is very important. Now, if you look at the model of how the GPU as accelerator works, you have the host, you have the device, and you need to move data from the host to the device. So that's the first hurdle that you need to jump. This is the first point where the bandwidth is limiting the performance that you can get. And then the second jump is once that you get the data on the GPU, you need to move it to the GPU chip. And that's the second jump that you have, because the speed of accessing data, how many clock cycles it takes to access data from the GPU to global memory is around 600 cycles. So if you are just waiting all the time and don't have anything to do, it will take 600 cycles of the GPU not doing anything in order for data to arrive for doing some calculations. So that's why it's so sensitive. So as already said, shared memory is very fast. Registers are very fast. And these are closely related to the thread hierarchy that I showed you before. Basically, each of the thread blocks allows you to take advantage of the shared memory by using collaboration. So all of the shared memory can be seen. Shared memory within a thread block can be seen within all the threads in that thread block. And all the threads in a grid can see the global memory at any given time, so they can sort of collaborate in that way in order to finish a big set of calculations that need to be performed. And in this way, we write to a basic set of extensions. And this is mainly the reason why I like CUDA. It's just that it's very simple. If you already know C, CUDA is not going to be anything new to you. It's just add a few modificators to the code that you might have, and it allows you to run on the GPU and take advantage of the parallelism that you have. So let's review probably the most important parts. You have function modifiers. You either can have a global function or a host function. Here, the most important one is the global, and it just says that a function that has been modified as it has a modifier as a global, it will be executed on the GPU. So that one will be running on the GPU. Then you have some kernel launch parameters, and this is what defines how many threads are you going to run, what's the size of the thread block, and how many thread blocks you have in a grid. And So that's the block size and the grid size. So that's just the number, the maximum number of threads that you're going to execute. And you have some variable modifiers that differentiate your function from a normal C function, and it gives you access to the shared memory. So if you look at the variable modifiers, you just have this shared modifier that means that that variable is going to live in shared memory. And at the very end, you have a synchronization of threads, and it allows you to set a barrier within your thread block. And I think that this is like the most minimum thing that you need to know in order to see some code and understand what might be happening inside a CUDA function. And of course, the manual for this thing is very huge. I just presented 5 or 6 of the extensions, and it's actually very big, and it depends on what you want to do, which ones are the ones that you need to use. But this should give you an idea of how is it, or a feeling of CUDA. So this is the last bit of the presentation, and I just have some code. This code that I have over here is actually oh no. Okay, give me a second. So right now I'm connected to the Yuma machine. That's the one that we have at Nagasaki, and I was just testing the latency. It's not that bad. So I should be able to show you on the fly. Okay, so I have one function, one program called Hello World stored in my local account back in Dejima. And I want to show you this code. Okay, and then I say set syntax. Let's see. Okay. So I hope that is it big enough for everyone to see clearly the code? Huh?
You can't see the comments.
Okay, so I can tell you what the comment says. Is it big enough? Is it? I can. Bigger. Okay. What about that? Is that good? Okay. I actually. How do you do that? No. I said it with C. That's what you get. Okay, so the first line that you have over here, or the second line that you have over here, is calling CUDA, and this is a CUDA library that has all the features that you want to use. The next line is your kernel function, and if you don't take into consideration this global variable, it just looks like a normal, well, almost. It almost looks like a normal C function. The only difference is that you have some special variables that are these ones over here that allows you to identify the thread block and the thread number for each of the threads. And this is what you use in order to differentiate the work that one thread is going to do with respect of another one. This function is very easy. It takes 2 arrays, some integer number, and it's going to add on these 2 arrays. So it's b equals a plus b, and b and a being an array. And each of these threads are going to just compute one element of the addition of these 2 vectors. So it's a very simple function, and this is what you can see here. So that's addition, and as you notice, this a single function is only going to compute one element at a time. But by using all the threads in a collaborative way, you can finish your whole work in just one instruction. Another thing that I have set up is that I limited the number of calculations or operations to perform to the size of the array, which is normal. So okay, we have a global function that will run on the GPU, and we have main function, and this is just basically a normal C function. I just declare some variables. This is all normal to you. I have some arrays that are going to be living on the host, and I'm filling up all the numbers on my arrays. So I'm adding some data inside of them. The next stage of this very simple example is allocating memory on the device. So here, memory is not the host memory and device memory are completely different, so you need to manage them independently. So the first thing that you need to do is a malloc. So if you are used to C mallocs, this is just a CUDA malloc. And it's going to allocate data to a pointer that I'm setting up that is going to live on the GPU, on the device, and it's going to be size int, and the number of elements is going to be n according to the size of my arrays. And I do the same for the second array. So this is all up to here. I think that is quite normal. Now the second step, once that you allocated the memory on the GPU, is to move some data from your host to the device. And this is the step that you can see over here. So you have a main copy. So you copy the data from the host. So this is host data to the device, and the amount of elements that you're going to compute, or the size of the data that you're going to move, is given by this number over here. And you need to tell the GPU that you're moving data. So this is CUDA mem copy, and this is from host to device. So very easy. And then it's moving data from A to A device, and that one is living on the GPU. And it does the same for B. The next step is to decide what's going to be your block size. So this is, if you remember the slides, just here, the block size is, so this is your block size. How many threads you have within a block, that's your block size. So you set the block size, and just for simplicity I set it to 10. And the number of blocks, of course, depends on the size of my array. I do some calculations so that it fits. And probably the most important part of your code is that calling the GPU and telling it to execute the data. So, okay, let's go back to. So I have my original function. This is my original global function that is going to be executed on the GPU. It's called add, and it just takes one array, integer array, a second integer array, and it will return everything in the second array. So here is my function name. The function is called add. I'm passing the parameters of the number of blocks and the block size. So you have this special notation to adding this information between three of these. How do you call this? I don't know. Less than, more than. So you add that information there, and it's just like calling a normal function, as you can see. The only difference is that all these calculations, all this function call is going to be executed on the GPU with the data that you already have moved to the GPU. And finally, once that this blocking call finish, you need to move the data, the results, back from the GPU to the device. And you do that in a similar fashion. You use the main copy that you used before. The only difference right now is that the last component, or the last element of the mem copy, is saying CUDA mem copy from device to host. So now it's the opposite direction. And finally, we just check that the results of the calculations right now on the GPU are correct. So I just do these calculations are happening on the host, and I'm comparing the results against the GPU results. So as you see, I'm storing the results on the GPU here, and then I'm comparing them there. Once that I finish, and I can release my data from the GPU, and that's pretty much the whole code. And as you can see, there is not really much that is different to see. It's just an extension to move data from and to the device and to execute each of your kernel calls. So it's pretty much what you would expect from C. The main difference here is that by adding this parameter here, you're actually telling the GPU to run all this work in parallel, and it's going to take advantage of the massive amount of parallelism that you have on a single GPU chip. So we can actually compile this just to show you that it works. So okay. Ah, G. Okay. Is it that one? Good. Okay, this is actually quite boring because, as you see, I don't have any printf. I just have an assert. So if anything failed, I will say it. And that's the normal way that I program. I don't really like printf. I just need one last. Oh, okay. So this is my export path for the for CUDA. So I now should be able to see VCC. So, okay, MVCC is NVIDIA CUDA compiler, and just by doing some exports and adding some environment variables, now I'm able to see the CUDA compiler. I do an ls. Okay, and I can see my GPU program. I do an NVCC hello world. I compile it. If I'm lucky, it should run. Okay, pass. And there it is. I have my executable, and shouldn't fail. Success. Oh well, that's a good question. Yes, there could be many. You have to trust me on this one. But tomorrow in the lab, all of you will have accounts on the GPU cluster that we have in Nagasaki, and you can test if what I said is true or not. Yeah. Okay. And if you find a bug, I will give a beer to anyone that finds a bug. To the first one. Yeah, it wouldn't be fair if everyone finds the same bug.
1 beer per bug?
Yes, 1 beer per bug. So that's about it. Any questions? No? Yeah, I thought so. It's very easy. Okay. Yes.
You talk about 3 types of memory.
Yes.
I think we saw only 2 because we copied to the device.
Oh yes.
You say that the resistors were the local ones.
Okay. Yes, I think I can show it in the code. Yes. In this case, I didn't went into the shared memory because that is just a bit more complicated. But okay.
These copies were the global.
Okay, if we look at the original function, this integer that is over here is going to be living on the register space. And so once that you compile your code, you can actually see how much registers each of the threads are going to be using. And that's some information that you can take into account where calculating how many threads are going to be executing on each of the stream processors at any given time. And that's actually going to limit the maximum number of threads and the amount of resources available for each of the threads. So this is a register, and if I just want to create, okay, in my experience, whenever I change code live, it doesn't work. So let's say int share bar. No, this is not going to work. Okay, I shouldn't try it because if I don't have it in my mind, I shouldn't do it. It's going to fail. But basically, if you have a shared variable, what you do is just declare with this share modifier, and this variable is going to live now on your shared memory. And that's pretty much everything that there is to it. Now you can move data from global memory, from registers to shared memory, and from shared memory to your local registers. Now the way that you avoid collisions, like all of the threads trying to access to the same variable. Okay, so if I just have this shared int bar, shared bar, that variable is going to be seen by all your threads. So if you modify something, one of the threads modify this variable, everyone will see this modification. At any point, actually, unless you put some synchronization point. So that's why I didn't really want to go into more details, because it actually involves more pieces of the puzzle. But what I wanted to show you in this very brief, I think I passed my time. In this very brief time is just that this is very simple. It looks like C, and if you already know C, you shouldn't be intimidated on starting using CUDA. And I think that's one of the biggest benefit of CUDA. It's just that it's very normal. Yes?
You can make a shared variable that's also an array, and then it will be actually blocked and be aligned with the
Yes.
like the block. So that would be an actual thing, right? So each,
Yeah, something like
each multiprocessor has its own shared.
something like that.
Yeah.
And then, well, the problem is that then I will need to move n outside to do a define.
So yeah, but still, then would mean that each multiprocessor would have its own shared variable.
Yes. Pretty much you can work it as any normal variable. It's just that it's living in a different namespace, a different memory space. Any other question or comments? Yes? The slides? Yes, that's a very good question. I actually have seen the architecture and I have seen the design, but I have really no idea of the significance of having two schedulers. So I cannot really give you an opinion on that. Sorry about that. Does anyone knows why is it that we have two schedulers on the Fermi? No. But basically, at least for me, it works the same. It's kind of a good question. No. This is completely hardware. You don't really have access to that feature. So I bet that this is for performance features, to keep all the machines busy. The multi-threaded part. But the exact implications of having two work schedulers, I don't know. Yes? Could be. It very well could be. But I have worked with a little bit with Fermi and mostly with GT200, and I think that the main difference between these two GPU chips is that you have a huge amount of dual precision capabilities. So this is something that I look at that is very significant. You have ECCC, ECC, and you have L1 and L2 cache. So those are the main features. I will ask the guys from NVIDIA and about this shared memory, and I will just about these schedulers, and I will let you know. Yes?
If you have a computation that purely doesn't use data, so are you completely bound by the bandwidth of the device?
Yes. Yes. You have. There are not too many possibilities. So you're either bandwidth limited or computational limited. And if you're not limited by any of those, you're doing something wrong. So, so that's why you have metrics for looking at what your algorithm is doing, or what your code is doing. Yes?
Maybe that since Fermi supports concurrent execution of
Right.
different kernels,
No, it's not that.
now it makes sense. No?
Andreas said no. So I think I will believe Andreas.
I think it has to do with how many issue ports there are towards between like the schedulers and the function unit. And there are just like more program cameras and more things like that.
Well, we have a very good bunch of guys from NVIDIA around here, so I will go there and chase them. Okay, I think I need to finish because then Matt won't have any time left. Yeah? One more question, if there is one. No? Well then, thank you very much.